Hello, welcome back here. My name is Al, and this here, well, actually, the title of this playlist is really corresponding with what it is at the moment. Uh, this is having to do with Euclidean geometry, traditional Euclidean geometry, right from the book. Well, not the book, but a translation, I suppose, that I've been using that I found on my hard drive, and I don't remember where I got it from originally. It might have been from a torrent or something. Anyway, it's quite useful and has pretty colored diagrams and so on. And right now, the bit that I'm working on here, trying to explain, is not in the book, and either it was an oversight of Euclid's, which is very possible, even likely, having to do with triangles having the same sides, all of the same sides, but not having their sides in the same order. You may think that's impossible, but if you examine these two pictures, you'll notice that it is possible that the order be different, because one can be a mirror image of another. You can't turn a mirror image into its mirror, the mirrored mirror, by simple rotation. The only way that you would be able to change this into this would be to lift it out of the plane and put it back in again, which we're not allowed to do. The axioms don't allow us to do it, and it says pretty explicitly that all the figures in Euclid's, at least in the first 6 books, are assumed to be in the same plane. So, but that doesn't matter. We can construct. It's quite easy actually to construct a mirror image triangle from another triangle, but I don't intend to do that either. I'm assuming that that's been given, and I want to show that the angles are the same. Now the second part, this part I've already gone over. We've labeled the sides, and now I'm just going to give the proof that not only are those sides equal, but their chord. Okay, scratch that last step. My construction was wrong. Now, how does this happen to me every time? There's something about, no, it can't possibly be. Now watch this. Now it'll work. See that? This thing is in full screen, using up all of the screen space. And so is this. So what? Who cares? So somehow, those are the cases when the keyboard shortcuts stop working. So it's my guess that, see this bar here? that you can never get something in front of? Well, something gets in front of that bar, then the shortcuts stop working. They won't work anymore. Which is not the purpose of a shortcut key, is to be able to access something when you're not able to see or click on it. But anyway, I came up with another possible solution, and if this is incorrect, then I'll just drop it, and I'll say that it's intuitively obvious and is taken as given just by thinking. What's the word they use? A priori. It's an a priori truth. It cannot be reduced to anything simpler. It's just a fact that if you don't know it, you're an idiot. Anyway, now actually all this text at the top doesn't really apply to my new proof. In the old proof, I just showed for one set, A and C, but in this new proof, completely by accident, that I came up with completely accidentally, it shows all of them at once. Do this. In order to keep track of what's going on, I've put numbers beside with the A, B's, and C's, even though they are identical length. I'm going to do something with these things, which I'll have to show on a separate page. I'm going to build this thing, and I'm going to demonstrate that this is a mirror image of that, and will have been constructed from this. Same for this one. Okay. And therefore I will have a mirror image constructed from a non-mirror image, right? Or sorry, this is a image constructed from a mirror image, and this is a mirror from a non-mirror. Either way you look at it. And that will allow me to rotate, which does not alter the angles or anything, this mirror image one over top of this one, which is constructed from this one and has a vertex exactly in reflection from this vertex here down below. That is exactly the same distance properties in terms of offset from here and from here and from here. So to do that, I need it blank, really. First, I need a triangle. And my big problem, the reason I kept coming up with these wrong answers was because I can't seem to make a triangle that's not either a right triangle or an isosceles by choosing numbers. Now, let's see, 107, that's arbitrary. Now, maybe it would be better if I chose a smaller angle than I usually do. How about 20 degrees? And the length, I tell you, it's going to come out right angle or something. 65. So that does not, but that looks like it's definitely not going to be a right triangle or an isosceles. Okay, doing pretty good. Alright, I don't mind. Oh, but now look. It's almost an isosceles. The angles. I just changed the angle, that's all. Put that to. Oh wait, no. It's gotta be more. Yeah, 35. No. See, now I've hit an isosceles. More angle. 55. And then I'd do something and it would look like the thing is symmetric, and then I'd realize, well, it can't be symmetric. It can't be that every single triangle is an isosceles. How's that? It looks like a right triangle, doesn't it? I've done it again. Well, I could shrink. Okay. 45. 43. It looks almost like. I don't like this one either. I don't like. It's not a right triangle, definitely. Okay, no, maybe this might be pretty good. No, there's nothing to creating a mirror image of this thing that looks almost symmetric. Well, I can shrink this one. Hang on. 55. Don't become a right triangle. It's going to be a right triangle, isn't it? Why is it? No, it's not. No, it's not a right triangle at all. Okay, that's a good one. Right, all you gotta do to make a mirror image is get the compass out and do this. And then get it out again and do this. Okay, now I know that that's a mirror image, and it's it's trivial to prove in fact that it is. Actually, it's done already. Alright, so here we've got our mirror image triangles. First thing to note is basically what I just did. You saw that created a mirror image. Now let's just see if we can prove that to like a machine of some sort, to a robot. Now this construction has the property that the length of this side, oh dear God, the length of this side I'm about to draw is definitely the same length as this one, right? Has the same baseline, and the length of the red side has to be the same as this one, because it's also one red radial distance from here. So this has all the correct sides, but they're in the wrong order, as you saw. So therefore it is a mirror image exactly. I can copy this and it'll fit perfectly. See? Alright. So we can construct a mirror image from an image very easily, like that. So what I'm going to do is take this one, let's say we'll call this one the non-mirror, and the given mirror image, okay, it wasn't really given, I had to make it myself. So we like this. Nothing free. Okay, it's better if there's a little gap anyway. You can see better what's going on. Get in there. Whatever, close enough. Now, I'll repeat the same thing once again. I'm going to construct by construction. So that's what the labels are for. This one here was the mirror image, so I'm calling this, what was red? A or B? B? C was white. It's either A or B. It's A. And this one is A2 for no, A1, sorry. This is the regular, this is the mirror. So mirror is 2 and regular is 1. And so therefore this here is C2, which is white, and this is B2. Okay. That looks better out here. The 1s and the 2s. So now what I'm doing is I'm constructing something exactly like this, but not using it to do that construction. Okay. And so now I can draw these lines. Now, the point of this is that I want to compare the mirror image sides with the non-mirror image side. Oops. I want to be able to use that equals operator that was defined, superposition. So I want to superimpose on top of I would like to superimpose either a mirror image or non-mirror image on a reflection of something that isn't. Okay, this triangle, I know by the construction, has all of the identical properties as this one, right? The same distance from this vertex as this is. This is the same distance from this vertex as this is, right? And it's been constructed. Okay. Similarly, now I can get rid of this. I don't know if you understand why this step is necessary, but it should become obvious in a minute. Like, what's the difference, you're probably asking? Well, the difference is these ones that I'm constructing, I know have certain properties related to the things that they're constructed from, as in being identical in every respect, right? So this well, let's look at the two. No, this one, sorry. This is the non-mirrored triangle, and here is another triangle, which I've constructed from it down below. I'm not going to even call it a mirrored triangle. I'm just going to say that it has the same sides, and these angles must be the same just by symmetry, right? Well, I'm not supposed to use symmetry, but by construction anyway. The relative offset of this vertex from these endpoints is exactly the same, except it's on the other side from this one. That's all. That much I can say with certainty, because I know that this is one red radial distance from here, from this point, and this same point is one radial distance from this endpoint to here. So in every respect, distance-wise, this vertex exactly mirrors this vertex. Okay? Now, that means that this triangle is a duplicate of this one, a 100% exact copy of this one, right? I mean, it turns out it's a mirror image, but it's a copy. This was created by copying, not by some other means, and so we know that this one must have all of the same properties as this one, just by similarness or something. Similitude. It is all relative distances are exactly identical, so the inclinations must be identical as well, right? Now here we have a mirror image triangle. It was given to us, and we didn't make it ourselves. It came from some other type of construction, right? And I would like to compare that with this. But I can't compare that with this because I can't lay it over top of this. Instead, I've constructed an identical copy of this down here that is known to have all the same angles and sides. And then all I have to do now is rotate this thing, take this, rotate, and it will, at least one of these sides is going to coincide with one of these sides, because they're the same length. So I'll rotate this until B2 coincides with B1 prime, let's say. Then I invoke theorem 4, which says that all of these sides must coincide because there's only one possible way, with this, given the same base and same co-terminal or something lines. There's only one possible vertex position, so everything must coincide, and so therefore I've successfully applied the superposition, I believe, of this triangle onto this one. Okay, and then same for this one. So by the principle of superposition, they are identical in terms of their corresponding angles as well. Alright, now if that's a valid proof, I don't know, but I can't see anything that violates any of the principles and axioms. We're allowed to draw those circles, we're allowed to draw these lines, and so this construction is perfectly valid. The noticing of the fact that this line, or this A1 prime, must have exactly the same inclination with respect to C1, because of the fact that this point was essentially copied down below, right? I mean, in the same relative, in the same way relative to these endpoints. Okay, implies that the inclinations of here and here and here and here must be the same. Okay, and we wouldn't know that if we were just given this and this. We couldn't make that comparison unless we were able to pull this out of the page and turn it on top of this one, which I don't think we're allowed to do. But this isn't doing that. This is constructing a whole new triangle that has the same properties as this, and by deduction, the same relative inclinations with respect to C1, and we were able to superimpose this one on top of that, and here. And that's it. Okay, I'm fully satisfied now myself that as far as the axioms go, they support the hypothesis of superposition for mirrored objects, and we can at any point now imagine lifting an object out of, or at least a triangle, out of the page and turning it upside down and putting it back again. So I think that also has given us a new ability. Okay, that's it. That's my best go at it.